Hi, in this video, I'll be going through some remaining parts about sequences, and in the next video, I'll have moved on to series. So let's begin, because this part is quite an important part in understanding certain properties about sequences. So we know that a limit doesn't always exist, but there's this idea of a set containing all subsequential limit. And in the extended real number system, we know from what we've proven earlier that in the extended real number system, there will always be a limit for a subsequence. And so this set E is non-empty. And since it's in the extended real number system, it is bounded above and below. And so the supremum of this set and the infimum of this set exists. And we call this supremum lim sup and the infimum lim inf of the sequence. These are also known as the upper and lower limits. So the limit superior is the supremum of the set containing all subsequential limits. And it's an easy proposition to show that the lim inf will always be less than or equal to the lim sup, because the lim inf is the infimum of a set and the supremum and the lim sup is the supremum. And so equality holds if and only if the sequence is convergent. And the reason why is because if the lim inf equals to the lim sup, it means that all subsequential limits converge to the same value. And thus, by the proposition we have proven way back, this means that the sequence converges to X as well. And so, this gives us a characterization of when a limit exists when we know that lim sup and lim inf always exist. So when we want to prove what the limit is or show that the limit value exists, we can actually just think of the lim sup and the lim inf and see whether they match. If they don't, then the sequence does not converge. But if they do, then the sequence converges to that particular value. What's important to note is how we now find this lim inf and lim sup. And so we must prove this theorem that actually gives us a characterization of the different equivalent statements for what a lim sup and lim inf is. Just for our reference, this part is taken from Bertley and Schaubert, and the definition we have used earlier was taken from Rudin, but they are actually equivalent. And so how Bertley and Schaubert define is that the lim sup is the infimum of the eventual upper bounds. And this means that there exists a cutoff such that all the sequences are below this upper bound. And you just take the infimum of this set. And then there's another characterization that says that if given an epsilon, then any value larger than the lim inf, there will only be a finite number of terms in the sequence bigger than that value. And any value less than the lim sup, then there will be an infinite number of terms greater than that value less than lim sup. And that is actually the most useful and able to help us find what the lim sup and lim inf is, because we just need to test whether the value we want fulfills this condition. And then lastly, we can also say it is the limit of this sequence where is the supremum of xn, and n has to be greater or equals to m. So it's basically, you have the sequence here, you just take away from m, you just take the tail ends of the sequence, and then you take its supremum. And then you just keep taking, and then you find the limit. If S is the self-subsequential limit, then lim sup equals to the sup of S. And that's our definition. And so really, let's just prove the theorem. It's a pretty long proof because there are 4 parts. And we'll just do it in a circular fashion so that everything implies each other. Firstly, for A imply B, now we just given an epsilon. Because we know that x star is the infimum, it implies that there will be a V in the bigger set such that V lies, and the V means this eventual upper bound. So there is this upper bound larger than the lim sup but less than lim sup plus some epsilon. And this means that lim sup also belongs to V. Because the lim sup is itself an eventual upper bound of some subsequential sequence. And so there cannot be a finite number of terms such that the sequence is, there can only be a finite number of terms such that the sequence is greater than lim sup plus epsilon. And then on the other hand, if you take lim sup minus away something small, then it's no longer in this V because this is an infimum of the set already. So you're going like less than it, less than the greatest lower bound. So you're not in V. So there must be an infinite number of terms such that the sequence is greater than this x star minus epsilon. And that proves A to B. So now B implies C, because if we are given that B holds, then we can find a very big cutoff so that this M very big, then this UM will be less than some number plus epsilon, the lim sup plus epsilon. And therefore, the infimum of this set will be less than or equals to x star plus epsilon. And thus, because there's also infinite number where x star minus epsilon is less than xn, then we know that the lim sup minus the epsilon will be less than um, because this is the supremum. Hence, x star minus epsilon will be less than or equals to the infimum of And since epsilon is arbitrary, we can then conclude that x star equals to the infimum of And because is monotone decreasing, this means that the limit is the infimum. And so this infimum, x star, will equal to the limit of Hope that's clear. And before we move on to the last two, and now we'll move on to the last two. So C implies D because you're given a convergent subsequential limit. And we know nk will be larger or equals to k. And so when you collect all the tail terms at the end, x and k will be less than or equals to uk because uk is the supremum. And so the limit of this subsequential limit will be less than the limit of uk, which equals to lim sup. And so we're done for this part. And then we can conversely inductively choose our subsequential limit such that xnk will be in between the uk's, where one side of the uk is minus 1 over k plus 1. And we take the limit for all this, it shows that the limit of uk equals to the limit of xnk. And this shows that the x star will be the limit of xnk. And so x star inside will be inside the set of subsequential limit. And because x star is inside the set of subsequential limit, this shows that x star is the supremum of S. Because we already know that all the limits are below at x star. And then we now know that x star is also in this set. And this means it must be the supremum already. And then lastly, B implies A is because we have a set that is the supremum. Then given any epsilon, there can only be finitely many number of terms greater than W. And that's because you have a subsequential limit that approaches sub S. So it's coming to sub S, which is your lim sub, or we'll prove is the lim sub. So you're coming to sub S. So you cannot have infinitely many points that is strictly larger than W, or else you can't approach W. So there can only be finitely many points that are larger than W. And therefore, W plus epsilon belongs to V, because it will be considered an upper bound. And so lim sub will be less than or equals to W plus epsilon, because lim sub here is the infimum. And then on the other hand, because there exists a subsequential limit converging to a larger number than W minus epsilon, so W minus epsilon will not be in this eventual upper bound. And thus, we get the other side of the inequality. And since epsilon is arbitrary, we can conclude that W equals to lim sub. And so we have proven the equivalence of the different characterization for lim sub and lim inf. You can read other textbooks for different types of explanation to it, but here is what Bertley and Schauber has presented to us, and that's what we shall follow. What we really want to note is that there will always exist a subsequence that we can create that approaches lim sub, and so it exists. So an example of how we find lim sub and lim inf will be the given one. Xn equals to minus 1 to power n over 1 plus 1 over n. So like I say, the definition 2 allows us to actually find it, because we know that if we put the lim sub as 1, it fulfills this condition that there's only finitely many n's such that xn is greater than x star plus epsilon, and infinitely many for x star minus epsilon. And so we can do a easy tweaking to show that the lim inf is minus 1. And thus, because these two limits are not the same, that means xn does not converge. And so we're done with this part about sequences. Do practice more about lim sub and lim inf because they are very useful. And I'll catch you in the next video where I talk more about series. Bye.